In this physics tutorial, you will learn 1. The meaning of cross product of two vectors. 2. What does the cross product represent geometrically? 3. How to calculate the cross product of two vectors. 4. How to find the direction of cross product vector. 5. How to calculate the cross product in coordinates. 6. Which are some applications of cross product in physics? Introduction. In our previous physics tutorial, we discussed the dot, scalar, product of two vectors. It was explained that when two vectors are multiplied in scalar mode, the result is a scalar number. This seems a bit strange to understand, since we expect the product to be a vector considering the closure property of multiplication, i.e. the product of a multiplication belongs to the same set or category as the two factors. However, we saw that this is possible in dot multiplication of vectors. But, now that we have explained the meaning of dot product, it is much simpler to understand the other type of vectors multiplication, i.e. the cross vector product of two vectors. The meaning of cross product of vectors multiplication. Symbolically, the cross product of two vectors, A and B, is denoted by the symbol x. Geometrically, it represents a new vector, which is perpendicular to the plane on which the two vectors lie. Mathematically, the cross product magnitude of two vectors represents the magnitude of the surface area enclosed by the two vectors, A and B, and their parallel extensions, the area of the parallelogram formed by the two vectors, A and B. How to calculate the cross product of two vectors. From geometry, it is known that the area of a parallelogram is calculated by the formula shown on screen. From trigonometry, we know the following equation. Here, opposite side of triangle equals height of parallelogram, and the hypotenuse equals lateral side of parallelogram. Therefore, we obtain the equation as shown on screen. Substituting the base and lateral side with the lengths of vectors, A and B, respectively as shown in the figure on screen. From this we obtain the following equation. But we stated before that. And since it is obvious that the previous equation is true for magnitudes as well, i.e. From this we obtain the following equation. What is the direction of the vector product obtained by the cross product of two vectors? It seems as a kind of shortcoming the fact that by formula we can only calculate the magnitude of the vector product obtained by the cross product of two vectors. However, this issue is fixed by applying the drill rule, or the screwdriver rule. You may remember that if you have ever turned the screwdriver in the clockwise direction, the screw has moved linearly away from you, and when you have tried to remove the screw, you have turned the screwdriver anti-clockwise to make the screw move towards you. This is illustrated in the figure on screen. The same idea is used to determine the direction of the vector, C, which is the cross product vector of A and B. Thus, if we have to find the direction of C equals A times by B, we start rotating from A to B. In our example, this direction is anti-clockwise. Therefore, like in the screw, the direction of the vector, C, will be upwards as shown in the figure on screen. On the other hand, If we have to find the cross product, D equals B times by A, we must start rotating from B to A. In our example, such direction is clockwise, and based on the screwdriver rule, the direction of the vector, D, will be downwards. Look at the figure on screen. From the two previous figures, it is obvious that the vectors, C and D, are opposite. Hence, we can write the following. Cross product of vectors and coordinates. If the coordinates of the vectors, A and B, namely x, A, y, A, z, A, x, B, y, B, and z, B, are given, we can find the coordinates of the vector, C equals A, times by B, i.e., x, C, y, C, and z, C, using the following formulae. Example: three forces are acting on the same object placed at the origin of the coordinates system. The tip of the first force is at -2, 3, 0, and that of the second force is at 1, 5, -4. What are the coordinates of the tip of the third force vector if these three forces obey the rule of vectors cross production? Solution: before starting the calculation, the position of the two vectors, F1 and F2, is as shown on screen. Thus, the direction of the third for F3 will be determined by the cross product of the tip's coordinates of the two forces, F1 and F2. We get the equation shown on screen. Substituting the known values, F1x equals -2, F1y equals 3, F1z equals 0, F2x equals 1, F2y equals 5 and F2z equals -4, we obtain the following equation for the tip's coordinates of F3. Therefore, the tip of vector F3 will be at -12, -8, -13. This is illustrated in the figure on screen. Applications of cross product in physics. In physics, there are a lot of applications of vector cross product. They are much more than dot product applications. Let's discuss briefly some of them. 1. Moment of force, m, as cross product of force, F, and linear distance from the turning point, delta x. It is obvious moment of force is a vector quantity, as unlike work, it is obtained through the cross product of force and linear distance from the turning point. 2. Magnetic force, F, of a conductor at rest is a cross product of magnetic induction, B, and the conductor length, L, multiplied with the scalar, I, current. 3. Magnetic force, F, of a moving conductor as a cross product of magnetic induction, B, and velocity, V, multiplied with the scalar, Q, electric charge. 4. The angle between two forces F1 and F2 can be calculated using the cross product if the magnitudes of the two vectors, F1 and F2, and that of F1 times by F2, are known, and so on. Example: a conducting wire is placed between the two poles of a horseshoe magnet as shown in the figure. The magnetic field lines, the induction B, lie from the north to the south pole of the magnet. Electric charges flow through the conducting wire in a direction that is away from us to the sheet. To make the viewer have a better idea, the figure is slightly inclined. If the magnitude of the magnetic induction is B equals 4 Tesla, B equals 4T, and the amount of electric charges flowing through the wire is Q equals 6 coulombs, Q equals 6C. Find the velocity, v, of wire, both magnitude and direction, if it forms a right angle to the magnetic field lines. The magnetic force produced is F equals 0.2 N. Solution. From the figure, it is easy to see that we move clockwise from Q direction to B direction. Therefore, if you consider the wire as the handle of a screwdriver, and given that you are rotating it clockwise, the screw will move forward. Thus, in this case, the wire will move to left. Also, from the clues, it is obvious that the wire is perpendicular to the magnetic field lines. This means sin theta equals sin 900 equals 1. The magnitude of velocity is calculated by the equation. From the cross-product rules, we have the following equation. Substituting the known values, we obtain, given that sin 90 degrees equals 1, the following equation. Mixed product of vectors. As we discussed in the previous example, we may have to multiply the cross product of two vectors with a scalar. The result is still a vector, as the cross product gives a vector and the product of a vector by a scalar gives a vector as well. Another rule for finding the direction of the cross product vector: in the cross product we have the following equation. We can apply the right-hand rule to find the direction of the vector product, C, when the directions of A and B are known. Thus, if we put the index and middle fingers of the right hand as shown in the figure on screen. From this, we obtain the direction of the vector. Based on the drill, screwdriver, rule. The thumb shows the direction of the product vector.